1995 from the Institute for Space Research in Moscow. He then was here for 3 years as a CFA postdoctoral fellow. Since 1999, he's been a senior researcher at the Institute for Space Research in Moscow, and since 2001, he's been a SAO scientist here with us. He's currently the Deputy Associate Director of the High Energy Division. He's won several awards, including the Zeldovich Medal from COSPAR and the Rossi Prize at the AAS. He's an expert in a wide array of X-ray related phenomena in physics, including galaxy clusters, cluster cosmology, cold fronts and merging clusters, and has done an extensive amount of pipeline development for Chandra. So with that, take it away.
Thank you very much. It's very fitting to do this talk today because we are just in the process of starting a really serious effort to prepare this mission concept for the 2020 US Decadal survey. So I will talk about capabilities, science drivers of X-ray Surveyor, the work that already has been done on this mission concept, and at the end briefly outline the plans for the next few years. So X-ray Surveyor was conceived just after the 2010 Decadal as the next generation X-ray observatory that would be able to provide X-ray channels for great facilities that would exist in the 2020s. So that includes things like JWST, fully operational ALMA, 30-meter ground-based telescopes. So we want something that matches sensitivity and provides X-ray channels to study, the classes of phenomena that would be attacked by the greatest ground-based and space-based facilities in the other X-ray bands, in the other wave bands. So if I am to name one thing that defines X-ray Surveyor, that's its new generation X-ray mirror, it's optics. So we'd like to be significantly, vastly more sensitive than Chandra. So the mirror that we aim to build would be a factor of 30 higher, would have factor of 30 higher effective area with factor of 50 higher system throughput compared to Chandra. Just to give you a perspective, a month-long observation of Chandra Deep Field South can be done in 1 day with this observatory. Okay. It will have a larger solid angle for surveys. It will have a significantly higher survey speed, etc., etc., etc. So the question is, how do we build this mirror? So state of the art today is Chandra. Chandra is a set of 4 nested, very precisely polished shells. Its mirror assembly is made of mirror shells with about 1 inch thickness, thick glass. Okay, so it's a heavy structure, 1.5 tons, and provides 0.08 square meters of effective area. If you express this in square centimeters, that's 800. It sounds like a lot, but in fact that's the same area as the input aperture of 1850 Harvard Great Refractor, sitting in our building. Okay, with Chandra we are able to look at quasars at redshift of 6, do dark energy studies with galaxy clusters, constrain neutron star equation of state. You cannot do the science with a 15-inch optical telescope, right? So you can imagine what kind of advances we would be able to do if we build, so to speak, a professional grade mirror with a few square meters of effective area for X-ray Surveyor. Okay, I will not talk about optics technologies behind this approach, because in a couple of months we will have a PH lecture by a young member of our team, Ryan Allred. So come on April 14th to learn about the technologies, neat technologies behind this X-ray mirror. I will though talk about one piece of work that Ryan did recently, because this is one of the defining sort of one of the core advances of X-ray Surveyor compared to the current state of the art, and that's its optical design. So Chandra mirrors is a Walter 1 telescope. So it has a nice optical angular resolution on axis, but quickly as you move off axis, astigmatism, spherical aberrations develop, and so the angular resolution quickly degrades. So in fact, you have sub-arcsec resolution only within the central two arc-minute radius of the field of view. Okay, so you can only do nice images in a very narrow beam. With X-ray Surveyor, we are looking at a more sophisticated optical scheme based on the Walter-Schwarzschild optical design. It's a design that eliminates comma but keeps spherical aberrations, so there are lots of trade-offs to be studied, and it's a significantly more sophisticated analysis than a Walter 1 telescope. So Ryan did this recently, and here is what we expect to be able to achieve. So on axis, we will aim at reaching 0.5 arcsecond resolution. This is essentially defined by the quality of our mirror segments. Off axis, if we have a flat focal plane, then the angular resolution will degrade much more slowly than for Chandra. With the next generation detectors, we are expecting to be able to build a focal plane that closely matches the optimal focal surface for Walter-Schwarzschild design. So, for example, instead of one single big CCD chip or 4 chips in a wedge-like pattern for Chandra, we can have a layout of 5 by 5, smaller chips covering 20 by 20 arc-minute field of view. If we do that, these chips very, very closely approximate the optimal focal surface. So the angular resolution that we expect to achieve is shown by the solid line. So it's sub-arcsec out to 10 arc-minutes field of view. So essentially the entire Chandra field of view done at sub-arcsec resolution instead of the central 2 arc-minutes. That's a factor of 16 largest solid angle for sensitive surveys. You can only go sensitive if your angular resolution is nice. So combined with a factor of 50 high system throughput, that's a factor of 800 greater speed for sensitive surveys. So we're not talking about factor of 10 improvement of X-ray Surveyor compared to Chandra. It's for surveys, it's a factor of almost 3 orders of magnitude. So one way to express this is to plot things like the flux limit you can achieve in a given amount of time versus the area that you can cover. So this just puts X-ray Surveyor in perspective with the existing and future facilities. So this is the line for Chandra. This is the line for X-ray Surveyor. So along this axis, what you gain is the product of effective area and the field of view. Okay, so it's called grasp. The larger the field of view, the more you move these lines to the right. Your goal is to be down here. Okay, so the further to the right and the further down you go, the better. So, X-ray Surveyor would have about the same grasp as Athena. So if you want to do shallow wide surveys, we would be able to do that. These curves start to flatten as we go faint. This is because you start running into source confusion issues, and you start to be dominating by the background. X-ray telescopes, unlike optical telescopes, they are in normal operating mode. They are essentially background free. So if you gain factor of 10 in effective area, you gain factor of 10 in sensitivity. Okay, but you can only go so far down, because otherwise you will have more than one source per beam. Well, so the rule of thumb is if you have 30 beams per source, you start losing sensitivity and ability to identify sources. So Athena with 5 arcsecond resolution will be limited at around 2 times 10 to minus 17 ergs per second sensitivity. That's slightly above the current sensitivity limits achieved by Chandra. With X-ray Surveyor, we expect to be able to push this down by a factor of 50 before we start running into the background problems, and we don't expect to be running into the source confusion problems ever. Okay, for sensitive surveys, that's a factor of 1,000 difference between Chandra and sensitivity. So massive gains in sensitivity and massive gains in our ability to survey the sky. let me talk a little bit about the mission concept that we have in place. And I should say that when I talk about specifics, I talk about, let's call it a proof of concept. Proof of concept mission configuration. This is something that we put together with Marshall Space Flight Center. It just demonstrates that you can build this facility and it will weigh, a certain number of kilograms and will cost a certain number of dollars to launch and operate it. That's our estimates. Now, as I will mention at the end, NASA is starting formal studies, so this is our first iteration. The formal study should result in a more optimal mission in the end, so would be better. Anyway, so over the past year, a team led by SEO and Marshall, and we've done engineering work mostly at Marshall, came up with a mission design. Okay, so that's a spacecraft with an optical bench, instrument module, mirror module, fancy new generation solar panel, etc., etc., etc. So the study included spacecraft, instruments, optics, orbit, radiation environment, all the normal things you do when you estimate what it would take to build a particular astronomical mission. So to put things in perspective, a similar kind of analysis was done in the 2010 Decadal when they started talking about W-first mission. Okay, so that's the initial design. We looked at the X-ray telescope, what it would take to put it together, and we looked at possible science instruments, a suite of 2 detectors and 1 insertable grating spectrometer. Okay, so I'm just flipping the slides to let you know that we went into some, depths in estimating what this mission will be like. So if you look at the spacecraft, and if you know the picture of Chandra in your head, they look very similar. And that's not a coincidence. There are no spacecraft, turns out that there are no spacecraft requirements for X-ray Surveyor which significantly go beyond what has been achieved for Chandra. About the same mass, about the same power requirements, pointing stability. It's a slightly bigger out aperture, but still fits in the fairings of normal launch vehicles, etc., etc. So it's a Chandra-like spacecraft with a significantly better mirror and the next generation of science instruments. So Marshall folks looked at the costs. So there is a spreadsheet of how much it will cost to build and operate it. The point is, this number is very close to the inflated cost of developing Chandra X-ray Observatory. So this is a Chandra-like mission in terms of complexity, in terms of spacecraft requirements, and in terms of overall cost. It's a great advantage, factor of 50 to 800 compared to how you look at relative to Chandra, but it stays in the Chandra envelope in terms of complexity and cost. So it's Chandra-like and not JWST-like mission. Let's talk about some of the science drivers that define the most critical mission requirements. So the major topic that drives the sensitivity and everything else is our desire to reach into the high redshift universe, basically into the epoch of reionization and formation of galaxies. So what X-ray observations provide is the ability to look at the very first generation of supermassive black holes. So, of course, many of you know that there is a great mystery of how we can explain the existence of very, very massive black holes at very early stages of the universe evolution. So, this optical image is a redshift of 6 quasar with an estimated mass of 1 billion solar masses, and there's just barely enough time since the Big Bang to grow such a black hole through normal accretion channels. Okay, and no one expects that you can grow black holes continuously at maximum rate. So something must be happening to provide significantly massive seeds that bump these objects into the Crow's curve sufficiently early on, so then they grow by accretion. This object is imaged with Chandra. It's a very faint object in the optical and infrared. It stands out as a single brightest object in the field when you look at the same place in X-rays. So black holes are natural things to be observed in the X-rays, especially lower mass objects, because the peak of the emission shifts into the high energy band. So the sensitivities of X-ray Surveyor we talk about would be sufficient to discriminate between a range of possible models for black hole progenitors. So there are considerations for arguments for light seeds of the black holes. So large populations, 3-star producing 100 solar masses remnants at very early stages. Sustained growth, super Eddington growth of initial 10 to the 4 solar masses black holes, or maybe direct collapse of massive objects into something with a mass of 10 to the 5, and then subsequent more slow growth into production, into a billion solar masses black holes. So this slide illustrates what kind of data we would be able to get to nail down the nature of the earliest supermassive black holes. So this is a simulated JWST 2x2 arc-minute deep survey with lots of galaxies, and I counted about 12 galaxies at redshift of 10. If you look at the same object for 4 megaseconds, so Chandra type deep survey exposures with X-ray Surveyor, there will be lots of X-ray sources. But positional accuracy will be such that you can associate each X-ray source uniquely with a JWST galaxy, so you would be able to tell whether X-rays are coming from a redshift of 10 object or a redshift of 3 objects, etc., etc. So the sensitivity limits will be, for a known object, it will be 10 to minus 19 ergs per second per square centimeter. Corresponds to X-ray luminosity 10 to the 41 ergs per second, or a black hole mass of 10,000 at redshift of 10. So you really, in terms of detection sensitivity, you really go into the interesting range which is required to discriminate between 10 to the 2 or 10 to the 5 seeds of supermassive black holes. If you don't have a nice angular resolution, and you have an Athena-like 5 arc-second resolution, you start losing the ability to do the science because of confusion well above the interesting range of black hole masses. So this type of science essentially drives the kind of sensitivity limits you want to reach, and what we plan to reach with X-ray Surveyor will be equivalent to, say, observing the first accretion light in the universe. So JWST will see those galaxies, but most of the light will come from a population of early stars. It will be very hard in the JWST data to find emission from the associated massive black holes. In X-rays, what you see is mostly black holes and not stars. So first light in the universe with JWST, and the first accretion light in the universe with X-ray Surveyor. You can, with X-ray Surveyor, you can track the evolution of supermassive black holes from redshift of 10 to redshift of 0, and you can do lots of science tracking the growth from early objects through billion solar mass active quasars to billion solar mass dormant objects in the centers of galaxy clusters today. So you can not only detect the earliest populations, but also track their evolution to the present with great level of detail. So second area where we would like to make big progress is increase our ability to do high contrast imaging of faint extended objects. So this capability goes hand in hand with angular resolution and throughput. So limiting factors in this is the contrast relative to the background and ability to separate out point sources. So X-ray Surveyor is expected to retain a Chandra-like particle background because similar types of detectors, similar type of focal length. So per square arc minute on the sky, it will be same particle background, but the surface brightnesses will be amplified by the system throughput by factors between 30 and 100, depending on the exact energy where you look at. Okay, cosmic X-ray background will be resolved into individual sources, and you can mask them out, so the cosmic X-ray background will not be amplified by the system throughput. Okay, quarter keV particle background, which is a significant limiting factor in X-ray CCDs, can be reduced by a factor of 10 based on our experience with Chandra if you have fine pixels in the system. So by analyzing shapes of electron clouds from particle hits, you can eliminate a very large fraction of the quarter keV background. Okay, and with microcalorimeter observations, you can, in principle, remove the soft galactic foreground, which will be amplified by the system throughput, through essentially the same technique you do in the optical with the skylines. You just look between the skylines. So this is line-dominated emission. If you have a nice spectroscopic capability, you can look between the lines and eliminate the background this way. So overall, we expect that reachable surface brightnesses will be 1/30 relative to the current Chandra limit. So what it will do, we will be able to look at much greater detail at the hot ISM in the Milky Way, its interaction with molecular clouds and generation of the hot ISM by young stars. So this is a Chandra picture of the Tarantula Nebula. It will be, correspondingly much better picture if we have X-ray, when we have the X-ray Surveyor data. In terms of looking at diffuse baryons in large scales, we expect that the sensitivity limits will enable us to detect the cosmic web filaments in emission. So not through absorption studies and the X-rays or ultraviolet, but directly mapping the thermal Bremsstrahlung from ionized helium and hydrogen plasma. This is very nice because this is essentially unexplored area, unexplored volumes, incredible amount of physics going on in the form of shock waves and feedback from galaxies sitting in those filaments. So very rich area for discovery. And we also expect that we would be able to answer the galaxy formation, solve the galaxy formation problem, because we would be able to look at the hot halos around galaxies. So the galaxy formation problem is mostly that of the nature of feedback. Okay, so if you look at the galaxies, this is a numerical simulation. Galaxies are expected to be surrounded by gaseous halos. So it can be separated into several components: cold gas and cold material with temperatures less than 10,000 degrees. This is your ISM and stars. This is what you see with the optical telescope. Okay, it's about 40% by mass, by baryonic mass, tiny fraction of volume. These objects have been looked very, 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 very detailed at a very, very, very great detail with a whole bunch of telescopes. There's little to be done, I would claim, to do in this area with the next generation of telescopes, if you look at the galaxy as a whole. There's about 30% of baryons that are expected to be in the 10 to the 5 degrees temperature range. These are primarily tidal stripping tail of infalling satellites on the galaxy. Okay, so this is what is observed through the UV absorption. And then there is about 30% of baryons heated to X-ray temperatures, heated essentially to the virial temperature of the halo. This is the gas that has experienced feedback in the central and satellite galaxies. The feedback expels about 50% of the baryons outside of the optical radius. This is the process that defines the galaxy formation, and this is where most of the theoretical research is happening. So X-ray observations will be able to look at this gas directly, and so directly to directly constrain the nature of the feedback. Next topic. With next generation telescopes, we not only want to look at the structure of astronomical objects, but we want to understand the physics, what actually is happening in those complex objects. We believe that the key new capability to address, these questions such as what's happening in supernova remnants, particle acceleration in various settings, jets, hot, cold gas interfaces, and galaxy clusters. These are settings with rich physics, and to make progress, what we need to do is to introduce the ability to do high-resolution spectroscopy at fine spatial scale. So it's technically possible to build X-ray microcalorimeters with fine pixels. So if you extrapolate an equivalent of Moore's law for CPUs, for bolometers, X-ray and radio bolometers, then the required number of pixels to cover, this supernova remnant will be reached somewhere in the late 2020s. So we expect to be able to build an X-ray microcalorimeter that closely matches the field of view and angular resolution of the X-ray Surveyor mirror. So what this will do is essentially provide a it's supposed to rotate, but I don't know. Actually stuck in my presentation. No. Well, I only had 2 days to prepare this stuff. Let me do. Okay, here we go. All right. So, picture is very high, significance, but it does emphasize that if you are able to take a high resolution spectrum from each pixel in your image, you're introducing a third dimension to the data. You would be able to look at the chemical composition, kinematics, and so you learn a lot more about the physics in these objects. So a couple of examples of problems that you can solve. This illustrates solving the nature of energy feedback in galaxy clusters, so the famous cooling flow problem. So in centers of clusters, there's a lot of radiative cooling, but the gas doesn't get cooled to very low temperatures. So we believe that the AGNs are introducing a large amount of energy into the system, but it's unclear how exactly the energy is dissipated. So there are competing hypotheses such as, for example, it could be sound waves generated by the black holes propagating outwards, and in a viscous medium you can dissipate the sound waves and generate heat this way. A recent work suggests that no, maybe it is a turbulence in the stratified atmosphere, and so you generate turbulent motions by bubbles of relativistic plasma in those systems, and there is a healthy debate going on what it is exactly. Right, and this problem has to do with how black holes regulate their growth and growth of the largest structures in the universe. So it's an important problem. So very hard to solve with today's data, but it will be very easily solvable access to spectroscopy on the scale of those structures, arcsecond scales. So if it's sound waves, then the structures are primarily propagating in the sky plane. So there will be little or no motion along the line of sight associated with a propagating sound wave. The turbulence, though, in the stratified atmosphere is primarily tangential. So if you're looking at the layers of turbulence, we expect, in fact, a lot of motion. Right? So if we can cross-correlate velocity field with the gas density field in this setting, we will be able to tell exactly whether it's a turbulence or sound waves being dissipated. In objects such as supernova remnant, you can separate the image by chemistry and emission mechanisms. So, for example, in this image, this is Chandra. It's possible with Chandra, but it will be infinitely more possible with X-ray Surveyor. You can separate thermal-like emission from plasma from very thin filaments of energetic particles that has been generated by the shock wave, and the structure of these filaments tells you a lot about the particle acceleration mechanism. The third capability that we can introduce with X-ray Surveyor is high throughput grating spectroscopy. So for things like IXO let's talk about IXO. The key for grating spectroscopy is a combination of capability to focus X-rays very sharply and then disperse the beam with the grating spectrometer. Okay, so if you have a mirror system whose angular resolution is not ideal, then that immediately translates into the resolving power of your spectrometer, because we cannot put like in the optical, we can what's it called? We cannot put an opening on your source, right? With a small, we cannot put a slit on the X-ray source. Thank you very much. Right. So in the X-rays, the trick that a lot of people plan to use is to use the fact that the angular resolution in a section of a mirror is highly asymmetric. It's primarily extended in the perpendicular to the mirror surface. So if you disperse your spectrum parallel to the mirror surface and you only use a small fraction of the input aperture, then you can still have a nice spectral resolution even if your mirror is not that great. So X-ray Surveyor mirror, when we build it, will be great, and we can cover the entire aperture with X-ray gratings. So we can disperse the beam into a single readout, and this will result in a very high system throughput. So the instrument design that we have in place will result in a factor of 250 higher system throughput compared to Chandra, and factor of 5 greater spectral resolution. So if you combine the two, we're talking about factor of 1,000 to several thousand improvement in spectroscopic capability relative to Chandra. Where it's important in the soft energy band where the resolving power of calorimeters is not sufficient. So with calorimeters we can reach 5 electron volt, 2 electron volt, maybe 1 electron volt energy resolution. That's a resolving power of 1,000 at 1 keV. If you want to go down to turbulent velocity widths or thermal velocity widths in typical settings, we want to reach above a resolving power of 3,000. So it's important to have a high resolution spectrometer if you want to do the science. So these are three essential capabilities that we introduce: very high sensitivity, an ability to do spectroscopy on fine energy, on fine spatial scales, and high throughput, very high resolution spectroscopy in the soft band. We've had a science workshop this fall in Washington, D.C. in the National Museum of American Indians, so it's on the Smithsonian turf. There is a website There are some broken links, but most of the talks are available for viewing. You can Google this workshop site. So let me go through some of my personal picks from the presentation in this workshop to give you a flavor of science that has been discussed. And again, I emphasize this is more like a proof of concept or initial step. When we do the formal NASA study, then we expect to come up with significantly better demonstrations of what you can do with the capabilities that we build into X-ray Surveyor. So let's talk about a couple of spectroscopic applications first. Martin Ellis did this talk on spectroscopy of black hole outflows. So just one slide per talk. This is all I'm selecting. Of course, with Hubble, we have a very high-quality UV spectra of black holes, so we know about structure of outflows from the black holes for warm gas. Okay, so this is a plot of velocity structure. In red is what you get from today's UV measurements. In black, this is what you get with Chandra. So you obviously see a lot more structure in the outflow with the UV. With X-ray Surveyor, the quality of X-ray data will match that of the UV observations today. So you will be able to tell the structure of the outflow exactly, but for the hot gas. Black holes can launch a lot more of hot gas than they do warm gas. So this is an important reservoir for understanding the amount of energy black holes are dumping into their environment. So essentially, this is another constraint of the energy feedback from the black holes. Rachel Austin talked about various kinds of spectroscopy for stars. Okay, so her talk was on stellar dynamos, understanding stellar dynamos with high resolution spectroscopy. So the punchline is that when we have grating spectra with X-ray Surveyor of bright stars, we can start doing things like understanding the nature, the structure of magnetosphere and its interaction with stellar surfaces, interaction of magnetospheres of other stars with their planets, and etc., etc., etc. Ferial Ozel did a talk on constraining the equation of state of neutron star matter. So this is important for understanding physics of quarks and things like that. So there are several ways of essentially what you do is you constrain the ratio between the mass and radius of neutron stars, and there are several techniques that you can use with X-ray data to put these constraints. And if you have an access to 3 of these techniques, and you will have an access to all of the 3 techniques with X-ray Surveyor, you can very precisely constrain the mass and radius of individual neutron stars, even if they don't live in binary systems. So even if you don't have access to kinematics of these systems. Okay, the key for X-ray Surveyor is a lot of suitable objects for this kind of studies live in globular clusters. So you want to separate the neutron star emission from everything else. So it's key to have arcsecond resolution. Pat Slane talked about supernova remnants in high definition. For me personally, I think the frontier in this field is defined by the question of when we reach the level of data quality such that we can use the information on the structure and evolution of supernova remnants as a constraint to the explosion models. Okay, I think that with X-ray Surveyor, when we have access to detailed spectroscopy on fine scales, when we can disentangle the three-dimensional structure and chemical structure of supernova remnants, and when we have enough baseline compared to today's Chandra images, so we can start tracking expansion of those remnants, it's very likely that we will pass this threshold, and it will create a very, very important input to the explosion modeling, to the supernova explosion modeling. Andrei Kravtsov talked about implication of X-ray severe observations for galaxy formation models. So his talk initially was called Constraining Galaxy Formation. He called it Solving Galaxy Formation with observation of gaseous halos. So as I said, with sensitive X-ray observations, you can directly see the products of feedback operating in Milky Way sized galaxies. And so you can establish observationally, very directly establish the nature of feedback. So here is a slideshow of what different feedback models do to X-ray properties of hot halos around galaxies. So all these feedbacks produce about the same, very similar optically looking galaxies. So you cannot constrain these models by looking at the optical images. But the difference in the X-ray properties of those galaxies is very significant. So big difference in flux, big difference in morphology, and big difference in the angular size. So this kind of detections would be possible out to pretty high redshift. So for more massive galaxies, you can do detections with X-ray severe out to redshift of 1. Very detailed data you can take for low redshift galaxies. So the accumulated effect of feedback on the Milky Way type objects you can observe in very great detail at low redshifts, and you can start tracking this evolution to higher and higher redshift in more massive objects. In the Galactic Center, there is a lot of X-ray structure. One interesting observation is that there is a significant amount of X-ray reflection. So this is a map at the iron line, at the fluorescence iron line. So essentially, this is a cold material, and X-rays is produced by reflection of different kinds of sources shining on these clouds. So there is a fair amount of bright X-ray binaries in this region, and there is also a past activity of Sag star. Okay, so the scale for the time delay for reflection between Sag star and this molecular clouds is a few hundred years. So with baseline relative to Chandra, with detailed information on spectra and structure, fine structure of X-ray reflection from these clouds, you can do things like establishing a past history of Sag star emission and solving the three-dimensional structure of molecular clouds in this region, and probably looking at the activity of several bright X-ray binaries. Lisa Townsley, her talk was on star formation and feedback in the Milky Way. So this slide, the slide I've taken out, was called X-raying the bones of the Milky Way. So our own Lisa Goodman did a lot of work on this faint, on the narrow, very dense structure. They call it the Nessie. Okay, so this is like a cold and dusty backbones of the Milky Way. So the system of clouds and filaments defines the various centers of the spiral arms in the Milky Way. There is a lot of star formation happening in these dense regions. It turns out that it's hard to see individual stars with an infrared telescope. There is a lot of confusion. There is a lot of extinction. Some of the objects are far away. It turns out that you can do a lot of useful, you can do a lot of investigative work, let me say it this way, with the X-ray studies. So turns out that if you take a Chandra observation of some of this dense star formation region, then you find all of young stars as X-ray objects. Very high percentage of young stars. So you can then point your sensitive telescopes. When you build GMT, you can point GMT, and X-ray Surveyor will tell you where to look at to find, to take spectra of of the young stars in those regions. So with Chandra, you can only do the nearby clouds in this backbone system. With X-ray Surveyor, there will be enough sensitivity to cover the entire galaxy. Okay, so you can do dense star formation regions in the entire galaxy. So this gives you a flavor of a range of science that's possible. So I think it's the capabilities are so great that you reach beyond the normal boundaries of X-ray astronomy with X-ray Surveyor. So you should perhaps you should start thinking about the applications of this type of data for your field, and I think that we can significantly advance understanding of astronomical system across the in the entire range of astrophysical science. Okay, so let's talk about what happens next and how can you help. So NASA has selected, very recently, has selected 4 large missions for studies for the next decadal. So this is a list of 4, and there is an X-ray Surveyor line is one of the 4. Okay, so these missions will be studied and presented to the decadal surveys as a possibility for implementation in 2020s and 2030s. So the other missions are far infrared telescope, a mission to look at the habitable planets around solar type stars, a large UV optical telescope, and the project I'm talking about today. So what this study is, okay? NASA is incredibly efficient in creating, and thinking about the structure of the process. So this is how they see the structure of the study. Okay, this is astrophysics division director. Okay, this is a study team. There is an integrated review. There are observers and there are working groups which are not even shown in this diagram. So let me break this down for you a little bit. So STDT is a science and technology definition team. Is a team, let's say, a community-driven team of about 20 scientists who will take a final responsibility for presenting the case for the decadal survey and for directing science and technology trades. The study office is typically a NASA center. For X-ray Surveyor, it's Marshall Space Flight Center. The study office will do things for which STDT have no resources. Things like engineering studies, mission design, cost estimates, etc. So not to be outdone by NASA, we want to put another bubble in this diagram, okay, and we want to create a science support office here at SAO to help STDT with the important work that needs to be done. There are lots of great ideas flying around, but to really convert ideas into something that you can present in a bulletproof way to your peers, to create nice, presentations. There is a lot of technical work, and there is a lot of literature research, etc., etc. So let's say you have a nice numerical simulations, but you don't have resources to predict what X-ray Surveyor will see in your simulation box. The Science Support Office will help you with that. There is, you have an idea of exploring, such and such science question, but you don't have time, you don't have postdocs. Science Support Office can explore these ideas for you. Okay, I put a Smithsonian logo in both STDT and the study office. So we've been intellectually leading this effort for a number of years. So I think we have a strong claim for a strong representation on the community team. So if you would like to participate and haven't done so, you have until Monday to apply to NASA to be on the STDT. We also are traditional partners with Marshall for development and operation of the Chandra program. So we intend to keep this partnership for development of X-ray Surveyor. And Science Support Office is a local thing. So if you'd like to participate in this, you should talk to me. So the last slide, I just want to reiterate that this mission concept, it features leaps in capability, very large leaps in capability. So large area with high angle resolution and 1 to 2 orders of magnitude gains in all traditional capabilities, such as sensitivity, field of view, high resolution spectroscopy for point-like and extended sources. It will be scientifically compelling. With this kind of gains, you're bound to be scientifically compelling because you strongly push the frontiers of science, and so you can do really exciting studies from solar system to first accretion light in the universe. And I think you will have a revolution in understanding of physics of astronomical systems through this ability to do fine resolution spectroscopy on small scales. And we believe that it can be made very feasible. So it's a Chandra-like mission in terms of spacecraft, cost, complexity. Some new technologies for optics are already underway. And the pace of development is such that they will be proven to sufficient level before the mission goes into phase B. So it's a unique opportunity to explore discovery space and expand our understanding of how universe works, and we should make it happen. So please help. Thank you very much.
Questions for Alexey?
So I was very charmed by that figure that had the performance of Athena, Chandra, and X-ray Surveyor. And I wondered, is there anything Athena can do that X-ray Surveyor can't also do? I mean, is there a phase space that belongs to Athena in this model?
So we, okay. So I think we should, to answer this question properly, we should step back and look at some history. So when Chandra has been developed in 1990s, the essential capabilities that were missing in Chandra was an ability to do high resolution spectroscopy, high throughput, high resolution spectroscopy, and the second capability that was missing is sensitivity. Chandra was significantly more sensitive than anything else before, but it's still, as I said, a 15-inch telescope, right? So the philosophy that existed for a long time and that has been implemented in Athena was to say that the most important step to take is to do high throughput, high resolution spectroscopy. So the observatory is designed to do very detailed studies of relatively bright, isolated objects. It's not completely fair to say it can do spatially resolved spectroscopy also with 5 arcsecond pixels. But the theme is you do bright objects and you do high resolution spectroscopy. When Athena was designed, they introduced a second capability to do wide surveys. So Athena has a significantly larger field of view than we planned for X-ray Surveyor. So even though the grasp of the telescopes is the same, Athena does plan to do 100 square degree surveys, and my personal belief that it's not the thing to do with X-ray Surveyor. So the answer is phase space difference is a capability to do, and we probably don't have a capability to do spectroscopy. Calorimeter spectroscopy of really bright sources because of pile-up issues, and Athena can do that. So things like detailed spectra of bright AGNs you can do with Athena, but not with X-ray Surveyor, and you will do wide surveys with Athena, but not with X-ray Surveyor. So that's the most important difference.
So maybe I'm thinking too small here, and not even on a 10-year time scale, but I know that one of the big problems for cosmology with using clusters is the mass calibration. Would you expect X-ray Surveyor to just completely solve that problem? And do we have to wait for X-ray Surveyor? And if it will completely solve that problem, where will that come from?
So my personal view is that it can be solved before, will be solved before, and the way to solve it is by combining X-ray information with things like Vikhlinin mass measurements for galaxy clusters. You can trace a lot of galaxy cluster evolution, so maybe not for the cosmological purposes, but just to track their emergence and evolution from the very early stages. One of the science examples which I sort of went over was the bright quasars at redshift of 6 detected in the Sloan survey. They are very massive objects, so they are expected to sit at the centers of most massive halos existing at redshift of 6. So the mass scale of those halos is comparable to the mass scale of galaxy groups today. So we expect X-ray signal from host halos of Sloan quasars. Okay? In 300 kilosecond type of exposure with X-ray Surveyor, what you would be able to do is to separate the emission from the central quasar spatially, then resolve the structure, take its spectrum, so you determine in which kind of objects these quasars sit. Put it another way, you can start looking at the first generations of galaxy groups at redshift of 6 and then track their evolution today.
Hi. So I want to ask, what would be kind of the expected launch date, and what would be the overlap with JWST for especially star formation? You might want to actually do these observations.
So I think if you look at the sort of finding wedges that NASA plans for the next decade, the launch dates for this type of facilities will be very late 2020s or early 2030s. So formally, there's no expected overlap with JWST, but I would argue that you don't need simultaneous observations, so you can follow up the JWST deep fields, for example, right? So it will take some effort in coordinating and in designing JWST programs such that the subsequent facilities can go back and look at the same places, but you don't need to run those facilities simultaneously for most applications, at least.